Welcome to our short introduction of fluids in motion, or fluid dynamics. The study of moving fluids is quite complex, as you can see in the diagram shown to the right. We're going to be looking at less complex situations, and we're going to be making an assumption that our fluid is ideal. Let's first start off by talking about how we categorize the two types of ways that fluids move. We have steady flow, and steady flow is shown over here on this diagram. You can see a ball that's flying through a fluid like air, and these nice smooth curved lines here, the name that we give that is called a streamline. So these are streamlines, and this smooth flow is called steady flow, also sometimes called laminar flow. And we also have behind here, where you have this very chaotic and turbulent flow. It's very irregular. That is the turbulent flow. So over here we have the steady flow, and then behind here we have turbulent flow. The fluid motion can be categorized as these two types. Well, we're really only going to be studying the steady flow. Steady flow, by the way, is basically stating essentially that if you were to pick a particular point P along this streamline, the velocity of the fluid would be the same. As the particles pass through this point P, they would all be traveling the same speed. Doesn't mean that over here or over here would have the same velocity. It just means that at this particular point, any particles that pass through along here will continue to have the same velocity at that point as the particles pass through. Now, we are going to be making a large assumption. We're going to be looking at only ideal fluids. And ideal fluids are fluids that are non-viscous, so we're going to neglect the internal friction that we get from the molecules that rub against the exterior solid material. We're assuming that it's laminar or steady flow. We also make the assumption that it's incompressible, and that's a good assumption for liquids, but not so much with obviously gases. And then lastly, we assume that the fluid is irrotational, so it doesn't rotate the molecules. So in all of our problems that we're studying, we're going to be assuming that we have ideal fluids, so non-viscous, steady, incompressible, and irrotational flow. Okay, let's move into the two main principles. Well, we're really only going to discuss the one main principle right now. There are two main principles that that all moving fluids that are ideal follow, and they are basically based on two conservation laws. We have the conservation of energy, which we'll see later on with Bernoulli's law, and then we'll be looking at right now the conservation of mass. So conservation of mass leads us to a very important concept of the continuity equation that you can see down here later in the notes, this equation right here, where we have the cross-sectional area A of a fluid that is entering a pipe multiplied by its velocity that it's moving at is equal to the cross-sectional area here multiplied by the velocity. So as you reduce the cross-sectional area, the velocity increases. You may have experienced this before. If you've ever held a hose, for example, and watched the water come out, and then you take the nozzle and put your thumb and make that cross-sectional area smaller, then you'll see the water will start to jet out really fast because you've reduced the cross-sectional area to make the velocity faster. Well, that's all based on conservation of mass. Okay, so let's talk about that. Take a look at this situation where we are going to be looking at a fluid that is entering a pipe here, and there's a chunk of mass here. So there's this slug of mass here. We'll call that M2. And then that same slug of mass is leaving here. We'll call that M1. And if we assume that the mass is conserved, which it is indeed, then the amount of mass that enters this section of pipe, so delta M, divided by the time that it takes to pass through this little part, delta T, is going to be equal to the same chunk of mass, M1, over delta T on the other end of the pipe. So this mass flow rate stays constant. So as you can see, hopefully, that this slug of mass that is moving from the left side to the right side is stretched out to be longer in this section, in the narrow end section, and moving a lot faster. Okay, let's take a look at this mass flow rate concept now. We are assuming that the amount of kilograms per second is the same that enters the tube as it is as it leaves the tube over here on the right side. So this remains constant. Now you might see over here we're going to replace that mass with density times volume. Hopefully you recall that density is mass per unit volume. So we can rewrite this as the mass is equal to the density times the volume and replace that into here. And let me rewrite this over here just a little bit more here. So the change in mass over change in time is constant, but we're replacing the mass with density times volume over time, which is constant. And we know that we are assuming this is an ideal fluid that is incompressible, so therefore the density is remaining constant, and really we have the change in volume over the change in time is constant. So this basically means that the volume flow rate, R, which we represent for change in volume over change in time, is remaining constant. So that, by the way, is meters cubed per second is the SI units for volume flow rate. So that means the chunk of mass here, or that chunk of volume of this slug of water that is entering on the left side of the pipe is equal to the chunk of volume that is leaving the right side of this pipe. Now we want to rewrite this in a more appropriate terms because commonly we measure the cross-sectional area and how fast this fluid is moving. So now if you look at the volume of this, remember that volume is the cross-sectional area of this side multiplied by the length, which we'll just for now I guess call this L2, would be volume 2 and area 2. And the same thing over here for this slug of mass, we have volume 1, which is cross-sectional area 1 multiplied by L1. You can see from the narrow end, it has a smaller cross-sectional area but a longer length. But it is the same slug of water, so the volume of the slug of water on both ends is equal on both sides. So just like the volumes are the same, we have earlier assumed that they have the same masses as well, because we're all assuming this is based on conservation of mass. Now let's put this volume rate flow in terms of velocity now. And if you look at the velocity of the fluid at this particular entering point here, it's equal to that length L2 in here divided by t. So that velocity v2 is the distance traveled by the time divided by the time. Just like over here, the velocity 1 would be equal to L1 divided by t. So now let's replace that volume flow rate with in terms of cross-sectional area. And remember the volume is the area times the length. So we have the area times the length, and it's divided by delta t. So we'll just write t. And that is remaining constant. And length divided by time, if you recall, is velocity. Now, if both sides have the same density, then we can cancel out for both sides and really just say the area times the velocity that enters the pipe is equal to the area times the velocity on the end that it's leaving the pipe. And hence you get the continuity equation with the cross-sectional area A V1 equals A V2. So in essence, the equation of continuity shows that some really important things of ideal fluids. That the volume flow rate coming in is the same as the volume flow coming out because the mass flow rates are the same. And this should explain things like why the flow, the speed of the fluid is faster in the narrow sections over here. For example, if you were to ever look at say a faucet at home and you look at the water that is coming out, you'll notice that the water as it comes down faster and faster, you'll see that it starts to get closer together because as the speed increases, the cross-sectional area gets smaller. Maybe you've seen this as well with rivers where the river bend gets closer together and then you get the water starts to speed up and you get rapids. All right, and those streamlines that you get in here also move closer. So when you look at the diagram, we were talking about streamlines. If the streamlines are actually closer together, that is an indication that the fluid is actually moving faster as well. And this conservation of volume flow rate can be applied in a variety of problems. Like, for example, there's a little configuration that I've drawn up here where you have, let's say 10 units of volume flowing in here, and then 2 units of volume flowing in here, and say 8 coming out this way, and 1 coming in on this end, and say 4 coming out over here, and then you're like, oh, how much volume flow and what direction is that going in? And so hopefully one will realize that the volume flow rate that comes in, if you look at, there's 10 and 2 and 1, so that's a total of 13 meters cubed per second that's coming in, and then you have 8 and 4 that is flowing out. That's 12 that is only flowing out. Oh, well, then that must mean there's a little bit of volume flowing right coming out of about 1 meter cubed in. So another thing that comes from this rate of flow is the flow that comes into a sort of intersection is also equal to the rate of flow that leaves this intersection of pipes. Okay, I think you should be ready now to tackle the next problem.